Stress Corrosion Cracking, an overview. Lecture by Dr.G.Subramanian, Chief Scientist Retired, CSIR, Central Electrochemical Research Institute. Stress corrosion cracking is the cracking induced from the combined influence of the tensile stress and a corrosive environment. The required tensile stresses may be in the form of directly applied stresses or in the form of residual stresses. The problem itself can be quite complex. Stress corrosion cracking usually occurs in certain specific alloy environment stress combinations. For example, the figures on the right side, top one gives you the intergranular stress corrosion cracking of an inconal heat exchanger tube. The crack following the grain boundaries, along the grain boundaries, corrosion along the grain boundaries. The big figure, the bottom one shows you the stress corrosion cracking in stainless steel 316 chemical processing piping system. Stress corrosion cracking is a combined action of susceptible material, the corrosive environment, the tensile strengths. The tensile strength threshold value is greater than or equal to the threshold value. Common sources of tensile stresses are external sources, residual stresses, and concentration stresses. In the case of external stresses, it is caused by centrifugal forces and temperature variation. The residual forces are due to forming, heat treatment, welding, machining, and grinding. Concentration of stresses at the root of pre-existing cracks or notches. Crack initiation. Stress corrosion cracking is initiated by stress concentrations at defects on the material surface. The defect may be an existing material defect. The defect may also be the result of pitting corrosion, crevice corrosion, intergranular corrosion, or local galvanic corrosion. Crack propagation. The passivation film at the tip of the crack is broken due to plastic deformation. Pure and normally very active metal is exposed and will be attacked by corrosion. The growth rate will be a combination of corrosion and cracking. The crack starts to grow when the stress concentration at the end of the crack exceeds the threshold stress intensity factor for stress corrosion cracking. Brittle fracture. When the stress concentration at the end of the crack exceeds the critical stress intensity factor, that is Ki is greater than KIC, there will be a rapid unstable brittle fracture. Environments that may cause stress corrosion of metals and alloys. Material, aluminum alloys, environments, sodium chloride, hydrogen peroxide solutions, sodium chloride solutions, seawater, air, water vapor. Material, copper alloys, environments, ammonia in gaseous and aqueous form, amines, water, water vapor. Material, gold alloys, environments, ferric chloride solution, acetic acid salt solutions. Material, inconal environment, caustic soda solutions. Material, lead environment, lead acetate solutions. Material, magnesium alloys, environment, sodium chloride, potassium chromate solutions. Rural and coastal atmospheres, distilled water. Monal environments, fused caustic soda, hydrofluoric acid, hydrofluorosilicic acid. Material, nickel environment, fused caustic soda. Material, ordinary steels environment, sodium hydroxide solutions, sodium hydroxide, sodium silicate solutions, calcium, ammonia, sodium nitrate solutions, mixed acids, sulfuric acid, nitric acid, hydrogen cyanide solutions, acetic hydrogen sulfide solutions, seawater, and molten sodium lead alloys. Material stainless steels. Environments add acid chloride solutions such as magnesium chloride, barium chloride, sodium chloride, hydrogen peroxide solutions, seawater, hydrogen sulfide, sodium hydroxide, hydrogen solutions, condensing steam from chloride waters. Material titanium alloys. Environments red fuming nitric acid, dinitrogen tetroxide, seawater, methanol, hydrogen chloride. Ways of propagation of stress corrosion cracking. The cracks which propagate along the grain boundaries called as intergranular stress corrosion cracking, as shown in figures right side, the top. The first one shows you the SEM images of intergranular corrosion, wherein you can see the next picture next to it shows you the depiction of intergranular corrosion. That is, corrosion travels along the grains, along the grain boundaries, The thick black line shows you the corrosion occurs along the grain boundaries. That is intergranular corrosion. Next one is the cracks which run through the individual grains called as transgranular stress corrosion cracking, as shown in figures on the bottom side. First one shows you the image, SEM image of a metal experiencing transgranular stress corrosion cracking. The next adjacent figure shows you a thick black line traverse along the grains, showing that an example of transgranular corrosion, that is corrosion happening along the grains, cracks occurring along the grains. Identification of stress corrosion cracking. Visual identification prior to failure is difficult due to the typical tightness of the stress corrosion cracks. A low power hand lens will greatly aid determination. Detection of cracks can also be enhanced with ultrasonic, radiographic, or acoustic emission techniques. Preventive measures. There are a number of different ways to control stress corrosion cracking. The method used depends on the application and may involve changing the mechanical, metallurgical, and environmental conditions. First one, mechanical conditions. Changing the mechanical condition. That is, avoid stress concentrators, relieve fabrication stresses, introduce surface compressive stresses, and reduce operating stresses. Next one, changing metallurgical conditions. Change alloy composition, change alloy structure, use metallic conversion coatings. The last one is environmental conditions. Add inhibitors, modify temperature. Thank you very much for watching this video.